Hello everyone, welcome back to the Professors DuBois channel. This is Professor Victoria and Professor Corey, and today we're continuing our thermochemistry unit and we're wrapping this all up with enthalpy of formation.
I was just getting warmed up.
Nice one.
Yeah. So another way we can calculate the enthalpy of a reaction is to use what we call standard molar enthalpies of formation. So this is written as like a delta H with an F. That little F means formation in the, it looks like a degree symbol up here that usually up in the upper right. That just means it's standard molar. It's on a per mole basis. So what this is it's the enthalpy change for the formation of 1 mole, and this is really important, 1 mole of a compound directly from its elements. And we'll show you why that's important in a second. So remember that the delta H, we can calculate the change in enthalpy. We can't really measure enthalpy directly. So what we do here is we say that the elements in their standard state have a value, an enthalpy value of 0. So the difference is going to be our delta H based on 0.
Right. That's just set standard. It's not true that elements don't have any enthalpy, but we have to start somewhere because we have to only measure the change. So here we go. We've got delta H of formation for 1 mole, remember, 1 mole from the element. So here's an example. So if we wanted the delta H of formation for carbon dioxide gas, and that's important, the state is important. So this is coming from carbon and oxygens, and you notice how it's oxygen O2, that's its normal standard state, it's not just O. And if we form 1 mole of carbon dioxide, then our delta H of formation in this case is exothermic, negative 393 kilojoules per 1 mole of CO2. And similarly for carbon tetrachloride, we have carbon and chlorine, and we have to go with our diatomic chlorine gas, and to balance this, to make 1 mole of carbon tetrachloride, we have this reaction, and we have a delta H of formation for liquid carbon tetrachloride.
So these experiments have been performed for many, many compounds, and you can find them in books. They'll have tables of enthalpy of formation values, and this is where you can get into trouble with the state, because they'll have for instance, with the CO2, maybe there is a value for CO2 as a liquid in there. So it's important, if you're going to a table, to check those states. Now this is something you might have to do. You might have to write the enthalpy of formation of a reaction, or you might have to determine whether this reaction represents a standard enthalpy of formation reaction. So the reaction given does produce 1 mole of N2O4. This is good. But notice that the reactants are not elements. We have a compound in there. So this does not represent the standard heat of formation for N2O4. So let's do it correctly. The elements that make up N2O4 are nitrogen, which is a diatomic, that would be N2, and that's going to be in the gas phase. Oxygen is the other element, that's going to be O2 in the gas phase, and that's going to form N2O4. Now this isn't balanced, and these have to be balanced as well. So, and what's equally as frustrating is, in order to balance it, it has to be balanced so that the product is at 1 mole. So this is, sometimes you get into fractions over there on the reactant side.
That's okay.
It's okay.
It's actually imperative for this. Okay, so now we can use the delta H of formation from all of these 1 mole of these compounds to get at a delta H of reaction. So we have reactants and we have products, and we can look up the delta H of formation of all of those substances in our reactants and on our product side. And we can use those, we can get the difference between the two to find the delta H of the reaction. So we can't measure enthalpy directly, so we've set the elements at 0. So if we know where the reactants are and where the products are, if we subtract the two, we get the difference for the reaction itself. So let's show you what I mean by that.
Let's just take a little bit of time and talk about this symbol, this funny looking symbol. I think is that called an epsilon?
It's a sum is what it means to me.
That means sum, right? The symbol it's commonly used to mean
capital, yeah.
And sum just means add them up. And then here also the N and the M, these are just the coefficients for the different either the reactants or the products. So these are the coefficients used to balance the equation, or the number of moles. That's a good way to put it. All right, so here's an example. We've got a reaction, and now this reaction doesn't have to be a formation reaction. We're going back to regular reactions, but we can use enthalpies of formation of the reactants and products to calculate the delta H of this reaction. So the formula is going to be the delta H of the products. So we have two products, CaO and CO2. So these are given in in the question, or you'd look them up in a chart. And there are no coefficients in this one, so we would sum those two values, the Ca and the CO2, and just 1 mole of each. And then the product, I want to go back to my chart.
Okay.
The product is the reactant. Sheesh. The reactant has a negative 1207.6. That's from the chart. And just checking the states. You got to be careful with these. They're tricky. So we're going to do the products, the two products minus the one reactant. And we have this balanced equation with just ones. So we don't have any coefficients to balance out there. And if we do the math here, and this is one of those situations where we have minus a negative value. Can you write there, like when you have a minus a negative value, we can change that to plus a positive value. That's a neat little trick you probably haven't done in a long time. I
want to point out one thing here.
Sure.
So you multiply your delta H of formation, which is given in kilojoules per mole, right? Because the delta H of formation is for 1 mole of reactant or product formed. And so you multiply by the coefficient, which is the number of moles.
Yep.
So in this case, in all of these cases, it's 1 mole, and that would cancel your 1 mole. So you're left with kilojoules, not necessarily kilojoules per mole, because your reaction may or may not be on a 1 mole basis. So that cancels, and then all of these are kilojoules.
And I think I see a minor mistake on this slide.
Okay.
It's saying that the delta H of formation is equal to the sum of the delta H. I think that's delta H of reaction.
It is.
Those should all say reaction. That's what we're doing. We're calculating the delta H of the reaction. Why don't I see these things when I'm building them?
I don't know.
You know?
But we are using the formation numbers. Yeah. Very good.
So you want to try one?
Of course you do. Try this.
We've got the delta H of combustion, huh? So I think that just means this is a combustion reaction. It's still the delta H of the reaction for 1 mole of methanol. And look at this. This reaction balanced has a coefficient of 2. So that's going to be a little bit interesting. When we do the formula, we're going to end up with the value for 2 moles of methanol. We're going to have to divide that by 2.
Oh, I was thinking that they didn't provide this.
Yeah, right there.
I was going to give you a hint in what combustion was. Ooh, react it with oxygen and make carbon dioxide and water.
Yeah, so the balanced equation, we have 2 moles of the methanol. You might as well write it in.
I might as well.
So 3 O2s, 2 CO2s.
That would have been a good one to make you balance.
And yeah, ooh. I know. Maybe we save that one.
We might.
The values are the delta H formation values are given up at the top. And notice, and they told you this. Now, sometimes these questions won't tell you like the oxygen. And you're like, I'm missing data. Where do I find the value for oxygen? Because you forget that that's an element and it's 0. This one, they were actually pretty kind. And they said that it did equal 0. Because it's an element in its standard state. So lots of coefficients to multiply by. And when you get your delta H of reaction, now that's going to be for 2 moles of methanol. And notice how the question asked for the delta H for 1 mole. So we can use a mole-mole ratio or simply divide by 2.
Here comes the answer. There you go. So when you did your reaction and you did your equation, you would get that for 2 moles divided by 2. Your final answer is on the bottom here.
exothermic, and that's consistent with combustion. When we burn things, they give off heat, give off energy.
Yeah. If we had an alcohol lamp, we'd give off some heat burning it.
All right, so that wraps up our thermochemistry
It is.
unit.
That was the last one. Last one for thermochemistry.
Thanks for hanging in there.
Take care, guys. Bye-bye.